The spiders on Mars have been recreated in the lab. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Nerdy question, but have you ever wondered what created the Martian araneiform terrain, or what some people like to call the spiders of Mars? I know I have. Mc Keown, a postdoctoral fellow at NASA's Jet Propulsion Laboratory, joins us to discuss her experiences recreating this otherworldly geology in miniature in the lab. But first, we'll give you an update on our recent collaboration with Radiolab and the International Astronomical Union. Latif Nasser, who's the co-host of Radiolab, will let you know how you can cast your vote to name a quasi-moon of Earth. Then, Bruce Betts, our chief scientist, joins us for a look at a different type of seasonal feature on Mars, recurring slope lineae, those pesky RSLs. And just in case you're in a last-minute shopping flurry right now, I'll leave a link to the Planetary Society's 2024 Space Gift Guide on this episode page for Planetary Radio. We've got some wonderful things for purchase there for the space fans in your life, but also free links to cool space posters and the new NASA tabletop RPG. That way you can print them and make the holiday season extra spacey. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. In April 2024, I met Latif Nasser, the co-host of Radiolab. Their podcast uses investigative journalism to answer questions about deep topics, some of which are space-related. My friendship with Latif began when a typo on a space poster in his child's bedroom led him on a wild mission to officially name a quasi-moon of Venus, Zoozve. After I heard that episode of Radiolab, I had to bring him onto the show to talk about it. What I didn't know at the time was that it was going to spark a grand adventure for me and a bunch of other people as well. After the experience of working with the International Astronomical Union, or the IAU, which is the organization that oversees the naming of objects in space, the Radiolab team decided to extend that opportunity to the rest of humanity, and so began their collaboration to create a naming contest for a quasi-moon of Earth. Unlike regular moons, quasi-moons don't actually orbit planets. Quasi-moons are asteroids that share a similar orbital path and period to the planets that they're associated with, but they actually orbit the sun. From the planet's perspective, quasi-moons trace out strange paths on the sky, but from a broader view, they orbit the sun and hang out near their planet, dancing under the influence of gravity. Quasi-moons only stay near those worlds for a limited amount of time before they then wander off to their next adventure in the solar system. You know, they have asteroid stuff to do. The quasi-moon in this naming contest is currently known as 164207 2004 GU9. Just rolls right off the tongue, right? It's a classic gray rocky potato-looking asteroid that's about 500 feet across, and it's going to be one of Earth's little buddies for about the next 600 years. Since the Planetary Society has a long history of helping to name worlds and space missions, our CEO Bill Nye and I agreed to join the judging panel for the contest. We helped whittle down the massive number of submitted mythological names to the final list. And voting is now open. But keep in mind, it closes on January 1st, 2025, so you're going to want to get your vote in the next 2 weeks. Latif Nasser, the co-host of Radiolab, joins us next to discuss the contest and how you can participate. Hey, Latif, thanks for joining me again.
Oh, my pleasure. Thank you for having me again on this. I feel like we've been on this year-long odyssey together.
It kind of has been, and we're coming to a culmination here in that we've been talking about the quasi-moon, the whole adventure with Zoozve. Now you're in it with this naming contest with the IAU, and it is finally available to the public.
Yeah, it's live. Voting is live. So we got something like 2,700 names from almost 100 countries, and then we had this panel kind of winnow it down. So we have 7 finalists, and everybody and anybody can and should go out and vote. It's at radiolab.org/moon. And you can just literally pick the one you like best. And who knows, maybe you'll help name something.
It's not very often you get an opportunity to do that, especially for Earth. But it's a kind of complex process to name a body in space. So once you had all these names, I mean, let's just pretend that I wasn't a part of this naming panel.
Which we're so grateful for you to be there.
Yeah, that was cool. Me and Bill and I got to be a part of this. But what was the process of winnowing these down like?
So we got so many. And then basically we took out duplicates. We took out stuff that already there's already stuff in space with that name. One of probably the biggest criteria was they had to be mythological. So like a lot of them were names that I loved, like, of course, Moony McMoonface or Quasi-Mundo or what. There were like a bunch of really silly ones that weren't mythological in any way, as much as I wish they were. So we weeded those out as well. So by the end we had, I think it was less than 1,000. And then we factored in, we were like, okay, we're going to make a panel. It's too much for us to look at alone. And we wanted every name to be seen by at least 2 people, just for fairness. We found a bunch of people who were kind enough to volunteer their time to help us, vote and rank the names. And then once we had those names ranked, we all got together in a room, which you remember because you were there. We all got together in a room and kind of like people stood up one at a time and made a case. Like we had each name candidate, there were something like 20, had sort of a champion who would come out, who was someone who already voted on it and who had kind of read about it, researched it a little bit, like kind of just felt something for this name. And so they kind of made their case. And so each name got a hearing in a way. Then in that room, we voted and then we kind of ranked them. And then finally we sent those names off to the International Astronomical Union, who basically like pre-approved the top names. And then we also did for the names that were, from like indigenous people or cultures that are still alive now. A lot of them are like kind of extinct, like Mesopotamian names or whatever. But like a lot of the cultures that are around now, we then took the time to go find people, elders from those cultures, people like institutions that represent those cultures, and we sort of ran it by them. We're like, would this be good? Does this feel offensive to you? Does this feel like an honor? We want it to be an honorific, but like if it feels offensive, don't worry, we'll take it off. So we sort of did that. Yeah, and then what came out the other end were these 7 names.
I really valued that about being in that meeting. I mean, first off, it was this kind of who's who of in-space podcasting. So I'm sitting here going like, oh my gosh, is that, that I had a little fangirl moment. There are people from Star Trek and all these other TV shows. But we also had some people that were really thoughtful about the fact that we need to make sure that we're respecting people's cultures in this, that we want it to be something that honors their cultures, and really taking an eye to diversity and making sure that we're being thoughtful about this process. I thought that was so valuable.
I was really impressed at how seriously people took this. Like even when the champions were sort of talking about like people brought in stuff from their own lives, and it just felt really like people, like it had a lot of heart. Like people brought a lot of themselves to it, and that was really inspiring.
People really did care about it, and I'm hoping that people out there looking through the website and seeing these names see the care, because there's a deep connection between the mythologies of these names and the idea of this quasi-moon. Like whether or not it was the people on the panel judging or the people who were submitting these names, there's already so much love that's been poured into this. I cannot wait to see who wins.
Yeah, and you could see a lot of the like almost themes that sort of came up through. Like a lot of the names were like tricksters or shapeshifters or kind of these liminal figures, like in a time of twilight or between life and death or between light and dark or between human and not human or whatever, like all these kind of like in between figures. Like it was such a fantastical array of names and from so many different places. It was really, really an impressive. We put out this name call out and the world showed up, And so I hope people will find that, and they'll find one that really speaks to them.
How long do people still have to vote on this?
It's for basically the entire month of December, so until the new year, until January 1st, voting is open.
And what happens after that? And now you got to, actually award it. Are you going to have some kind of ceremony or something?
Yeah, there's a date in January where it's going to get announced. And the IAU has this bulletin that it puts out, and that's where it'll be first announced. And then at the same time, hopefully we'll announce it on our podcast. And you guys are obviously free to announce it. But we are poised to come out with actually like a great name out of this one. I'm really excited about it.
I'm really looking forward to it. And thankfully, at least for the judging part, most of the hard work is done at this point. Now you just have to sit back, watch people put in their votes and see what happens.
Yeah, it's true. And so this is the part that we are thinking of, like, we need to tell as many people as possible. We need to tell a lot of students. We need to tell people who wouldn't ordinarily care about this sort of thing. Like, this is the moment where it's like, go out and tell everybody because everyone's invited to the party.
Well, you heard him. Go out and tell everybody. I've been telling all my family members, all my
thanks.
friends, asking them to vote because this is a special moment here. You don't get to name a quasi-moon often. You don't get to name a body in space often. And this body's going to be with us for what? At least 600 years?
At least 600 years. So it's definitely, how many generations is that? Like, yeah, this thing is going to outlive you, and it's going to outlive everyone alive on planet Earth right now.
Well, I'll put, as usual, a link to the actual voting for this on this webpage for Planetary Radio. And thanks again for stopping by and being on this journey and sharing it with all of us, because I had so much fun even just hearing about the initial Zuzve situation. And now here we are naming a quasi-moon.
Well, thank you. I feel like you and your show and your listeners and the whole Planetary Society here, like you all have been cheerleading us. And yeah, it sort of puts wind in our solar sails too, So thank you.
Well, thanks for doing this. And I hope when we finally have the name selected, you'll come back on and announce it to everyone.
Oh, yeah. Oh, my pleasure. Oh, I can't wait.
Thanks, Latif.
Thank you. Thanks so much.
The surface of Mars is a dynamic place, and scientists have found many curious features that are unlike the geology of Earth. But that makes sense, right? There are a lot of processes that happen on Mars that don't take place on a nice, watery, temperate world like Earth. Today, we're going to take a look at araneiform terrain, what the headlines like to call spiders on Mars. But don't worry, there are no actual spiders on Mars that we know of. But these branching formations do look very spider-like. Araneiforms were first observed in 2003 by orbiting spacecraft. The prevailing hypothesis is that they're created by seasonal sublimation of carbon dioxide ice, also known as dry ice. In winter, carbon dioxide condenses from the atmosphere onto the surface of Mars, forming a layer of translucent ice. You'll see it primarily at the planet's poles, but it also happens in other locations. In the spring, sunlight penetrates the ice, warming the ground beneath it and causing that ice to sublime from the base and turn into gas. The gas builds up pressure, cracks the ice, and erupts, carrying dust and sand and leaving behind a spider-like network of troughs. This process of carbon dioxide deposing onto the surface, subliming from a solid straight into a gas, and changing the terrain around it is known as the Kiefer model. This model is widely accepted, but the exact processes involved are kind of unclear because we haven't observed this geology up close. You'll note that we've never sent a rover or a lander to the southern hemisphere of Mars. For good reasons, but that's a whole other topic. What's important here is that the araneiform terrain forms in the south, so we've never been able to study them up close. But for the first time, a team of researchers at NASA's Jet Propulsion Laboratory have successfully replicated the formation of araneiforms in the lab. Today, I'm joined by Dr. Mc Keown, the lead author of the paper detailing these experiments. Lauren is a planetary geomorphologist from Dublin, Ireland. She studies the icy surface processes of worlds like Mars and Europa in the lab so that we can then compare them to the results of spacecraft data. Her team's new paper, a lab-scale investigation of the Mars Kiefer model, was published in the Planetary Science Journal on September 11th, 2024. Thanks for joining me, Lauren.
Thanks so much, Sarah. It's great to be here.
So I remember it was, I think, 2003 when the first stories about these spiders on Mars started happening. And anytime it's one of those things that's kind of freaky on Mars, I saw a face, I saw a pyramid, it's going to hit the news, right? But these aren't actual spiders. So what are we talking about here?
Yeah, they were later called the more scientific term araneiform to try and get away from media articles saying that we found spiders on Mars. But colloquially, we refer to them as spiders because they're these strange radial features that have legs. And so they reminded people structurally of spiders.
How big are these things?
So yeah, they can be up to 1 kilometer in size. Yeah, they vary greatly in their different morphologies, how they appear, the amount of legs that they have, and their overall diameter. So they range from a few tens of meters to over 1 kilometer.
Do they happen everywhere? My understanding is we found them mostly in the southern hemisphere.
Yes, mostly in the southern hemisphere. So the original spiders were found dotted around the South Polar Cap, and they were originally mapped in 2003. But in recent times, I think back around 2016, my collaborator Anya Purjankina found these other features called dendritic troughs, which are found on the regions in between dunes. And they look like spiders, so they're like a different type of spider, but they're actually forming and growing in the present day. My PhD supervisor, Dr. Mary Burke, found features called sand furrows, which form on the dunes. And they're kind of, again, smaller dendritic features that look a little bit spider-like. And they form in the present day, but they're erased by wind. But the ones around the South Polar Cap, it was originally proposed that they keep growing year to year, but in the last 2 decades of observing them, we haven't seen them grow or extend or newly form, those ones. So it's intriguing that we have these different types of spiders.
That is interesting, because if the larger ones aren't actually growing or multiplying as time goes on, does that suggest that these are actually older features that might have been caused by seasonal changes, but that the ones we're seeing are not being created year to year?
Possibly, yeah. That's what my current work in my postdoc research at JPL seeks to, probe at. It's possible because we see fans and spots emanating from their centers and from their legs each year, but we haven't seen them, the ones around the South Pole, grow or newly form. So that suggests that they perhaps formed during a past climate regime, and therefore understanding more about their formation could give us a window into seasonal dynamics in a past climate, which we don't know very much about.
And that's even more confusing when you get to the fact that it's in the southern hemisphere of Mars predominantly, because there are such different changes in elevation between the northern hemisphere and the southern hemisphere. Trying to understand those conditions a little better has got to be complicated, knowing that we can't even get a rover down there because it's much harder to land.
Yeah. So there's lots of different environmental reasons why they might be forming in the South Pole and not the Northern Hemisphere. Now, we do have the sand furrows in the Northern Hemisphere on sand dunes. And so the lab work that I'm doing at JPL is to try and understand the interplay between how the spiders form and their local conditions.
It's a really weird situation because it points to the fact that while Mars is so much like Earth, there are these formations of terrain that are so alien to us. We haven't seen anything like this on Earth, right?
No. Actually, I used to start out all of my papers with the line, spiders are unlike anything seen on Earth. And I don't want to divert too much from the topic at hand, but in the last few years, I became really interested in features called lake stars, which are pattern-wise, they look like spiders. They're dendritic features found on lake ice on Earth, and they form by a totally different process, but they're very similar in pattern to spiders. And so in keeping with being, the only research I do, this very one particular pattern in nature, I started studying those features as well.
I hadn't seen anything like that until I was reading your paper, which is interesting because they're clearly created by very different processes. On Mars, a lot of these features are created by CO2 ice, and we'll get into that. But I really do encourage anybody listening to this, if you can, to check out this paper, because the images of the lake stars versus all of these weird spider formations, it's really cool to see.
Thank you.
How did you get into this topic of research?
So since I was about 13 years old, I wanted to be a planetary scientist. I saw a news report on the detection of Enceladus's plume, and that fascinated me. I remember walking by the TV and seeing the Irish news at the time. My mom was watching it and just seeing that this small icy moon had this giant plume emanating from it. And I thought, wow, that's fascinating. And I started going on the NASA website and learning more all the way back in Ireland. And then I studied physics with astronomy at university, and I became particularly interested in icy surface processes. So, stemming from Enceladus, it led me to Mars. So my PhD supervisor had just moved back from the States to Ireland, and I ended up working with her, and she had an awesome project on features called linear gullies on Mars, investigating their formation. So actually, my current postdoc advisor, Dr. Serena Denega, was working with Mary, and they were testing the sliding CO2 block hypothesis, which suggested that chunks of CO2 were breaking off sand dunes and sliding down dune slopes to create these really strange sinuous features called linear gullies. So sinuous to linear. And my job in the PhD was to test the formation of their terminal pit in the lab. So basically getting blocks of dry ice and putting them in a container that was evacuated of any humidity, and putting them in a container on a bed of granular substrates of sand-like material, and investigating whether the CO2 would burrow and form these pits that we're seeing on the sand dunes. And then one day I was running an experiment, and I gently lifted the block up, and Mary said to me, "Do you know what those features are?" There were these strange, sinuous dendritic looking channels beneath the block. And I was like, that's cool, And Mary said, do you know what those are? I said, no. And she goes, oh, they look like sand furrows, the features I study on Mars. And I was like, oh, wow. So I went down a rabbit hole, and then I started becoming obsessed with furrows and spiders. And then the course of my PhD project changed. So it was actually kind of an accidental discovery, which was wonderful. So I got to research the linear gullies and then spiders. And I was introduced to some of the key researchers studying them. Candy Hansen, it's been an honor to work with her. And Sylvain Picu at JPL as well, the original person who mapped the spiders. So eventually, after the PhD, I got in touch with Serena to ask, could I do a postdoc project with her? And so we banded together a group of us to put in for a NASA proposal to research spiders further. And so the main goal of the project was to try and understand the role of different environmental constraints on their morphology and activity. So things like grain size, whether there's dust in their surrounding atmosphere and then forming in the ice, whether there's water ice within the top layer of substrate, that sort of thing. How does that influence the morphology and relative activity of the spiders? And in turn, then, can we use what the spiders look like to understand more about their local conditions where they formed?
And that's the key right there, because these aren't popping up all over the place, right? There must be very specific conditions locally that are creating them. It is mostly this carbon dioxide ice. So how does it form, and in what conditions do we see this happen? So
Mars's atmosphere is predominantly CO2. It's about over 95% CO2. And in winter, it descends on the surface in the form of ice and frost, different frost types. And then in spring, it sublimates or changes directly from ice to gas. And so that seasonal cycle forms a lot of unique features that we're not totally familiar with here on Earth. We might have similar analogs, air quotes analogs, but because we don't have that process occurring naturally on Earth, that's why we need to do analog lab experiments and try and recreate CO2 ice in the lab.
And the reason it's creating these features we don't see on Earth is because it's subliming and not because it's just kind of melting?
Yes. So it's changing directly to gas on the surface, and that causes a lot of things to essentially go poof, and it disrupts the surface, and you get all sorts of weird and wonderful seasonal dynamics.
It wasn't until I was reading your paper that I learned about the Kiefer model, which is what you're using in order to basically figure out the steps of how these things are created. Could you talk a little bit about what the Kiefer model is and what those steps are?
Sure, yeah. So the Kiefer model is the main model proposed for the formation of spiders on Mars. So in spring, it was noticed that there's a lot of dark fans or spots appearing on top of the spiders. So you've got these, very beautiful dendritic spider-like patterns, and then these dark blotches appearing above them. So it was suggested that the spots were appearing on top of translucent ice on top of the spiders, because the locations of the spiders were so cold that it appeared that there was actually CO2 there. Even though it didn't look super frosty, it was actually transparent. So the Kiefer model suggests that in winter, translucent slab ice appears on top of the spider locations. And then in spring, sunlight penetrates the ice and warms the regolith beneath the ice. And this eventually causes the gas or the ice at the base of the slab to turn to gas. And then this causes a pressure buildup, and eventually the ice cracks. And the gas beneath the ice then rushes towards the crack, and so in its wake it carves these dendritic channels. This is high velocity gas, so it entrains the regolith beneath the ice and deposits it on the top in the form of these dark fans and spots that you see in spring. So that's basically the Kiefer model.
But these formations are really big. If you could stand on the surface of Mars in this place, say 100, whatever number of years it's going to take for us to get there, do we know if it's a less impressive process, or would you actually be seeing material spewing out of these things?
That's a really great question, and I would love to see a plume. The process of the material being excavated and then transported on top it's transported in the form of a plume or a geyser. I'd love to see one in person from a side view. Specifically Candy Hansen has been leading the effort to find plumes in action over the years, but they're very elusive, and there hasn't been any strong definitive evidence of plumes in action. So some of them might be too diffuse really to catch, and then it's also an issue of timing as well in terms of seeing them. But it is an interesting question as to whether they're very explosive or diffuse, and also in a past climate regime they possibly could have been more energetic, and the spider patterns could have formed in few events, or else today they could be forming in multiple episodes, but the spiders might be growing at a rate that's too slow for us to detect as of yet.
There are so many processes across the solar system that I just wish we could go see in person. These kinds of creations, but also the plumes on Enceladus, or if you could stand on Io without bursting into something, it would be just amazing. But it's startling how much we just have to keep in our imaginations, and we can't go to visit yet.
Yeah, but we can see a lot of these processes with the orbiters, and specifically HiRISE has given us a great view into, the seasonal changes occurring on Mars. And some of those images are beautiful. I'd encourage your listeners to look up HiRISE and to go on the website, and you can look at some stunning images of seasonal change.
That's a thing too. I wonder if there's actually any instances of these formations forming that might be hidden in the data, but we just haven't been able to come through it yet because there's so much imagery from HiRISE.
Yeah, possibly. Actually, during my PhD, I was looking for pit growth. Again, going back to the linear gullies, I was trying to see, did the pits widen, year to year? So I was looking at trying to see if there's any change between the years. And in one or two images, and someone else had previously detected this, but it was cool to see new ones myself, where there was what looked like little chunks of CO2 actually caught in the act widening the pits. So in one image, you'd see a chunk of CO2 and then it was gone. And then, in later images, the pit had actually widened, which suggested that the CO2 sublimation, grew the pit. So that was cool.
That is pretty cool. How thick of an ice sheet are we talking about creating these? Because I imagine, it's hard to make an analog in a lab if you're dealing with these like macroscopic conditions that you're trying to shrink down. Yeah.
In the lab, we're dealing with a small scale, and that is an issue. You're trying to take something that's, the features are tens of meters to a kilometer in size, and you're trying to shrink it to, this small little box in a chamber. So, there are limitations there as well. In the lab, we've been trying to replicate the scenario, the Kiefer model for spiders, and trying to condense CO2 and grow spiders in the lab. And so we've been growing ice that is up to about a centimeter thick in the center in the lab, and we don't have huge bounds on where the spiders form and what type of thickness the ice is today, but it's much larger in scale, obviously.
We'll be right back after this short break.
Greetings, Bill Nye here. 2024 was another great year for the Planetary Society, thanks to support from people like you. This year, we celebrated the natural wonders of space with our Eclipse-orama event in the Texas Hill Country. Hundreds of us, members from around the world, gathered to witness totality. We also held a Search for Life symposium at our headquarters here in Pasadena and had experts come together to share their research and ideas about life in the universe. And finally, after more than 10 years of advocacy efforts, the Europa Clipper mission is launched and on its way to the Jupiter system. With your continued support, we can keep our work going strong into 2025. When you make a gift today, it will be matched up to $100,000 thanks to a special matching challenge from a very generous Planetary Society member. Your contribution, especially when doubled, is critical to expanding our mission. Now's the time to make a difference before year's end at planetary.org/planetary fund. As a supporter of the Planetary Society, you make space exploration a reality. Thank you.
It must be really difficult to kind of figure out when and how these things formed, given how different the climate on Mars has been. I was baffled earlier this year to learn how much the axial tilt of Mars changes over time. So that's got to make it really difficult to try to pinpoint when these things formed.
Yeah, exactly. So the climate has changed quite drastically on Mars over time, and these spiders could possibly be a window into seasonal dynamics in past climate regimes, which we don't know a lot about. So it's very interesting to probe their relationship with local conditions, and how does the ice thickness influence their morphology? Is there a particular ice thickness at which they stop growing, or which is more efficient for them to grow, and so on?
Yeah. At some point, ice must get so thick it's hard for the stuff to come out. But maybe then it's just more explosive and produces an even more pronounced situation.
Yeah, possibly there's an ice thickness at which the ice becomes too heavy and, it's not as explosive. There's probably a Goldilocks condition of ice thickness, translucency and grain size beneath the ice, and whether or not there is water already embedded in the top layer of the regolith.
How would the water change that interaction?
So we think that the presence of water ice within the pore spaces of the regolith would cause it to be less scourable, I guess. So if you have looser material, it's easier for a high velocity gas to just whoosh past it and train it. But if that's really cemented with water ice, we think that it's less conducive to spider formation.
Yeah. Given the way that the conditions in this area have changed over time, it probably makes sense to, instead of trying to figure out what the conditions are in present day on Mars that are creating them, it might make more sense to try to replicate it in a lab and then figure out at what point those conditions are met on Mars in order to determine when and how they form.
Yeah, and actually in the lab, we had some surprising results where when we were growing CO2, so we were flowing CO2 into a vacuum chamber. So the vacuum chamber is called DUSTY. It's a backronym. I got to name it. So that's one of my fun facts about myself.
Wait, you got to name Dusty?
Yeah, I got to name Dusty. It was one of my proudest achievements at JPL. So it stands for Dirt dirty under vacuum simulation test bed for icy environments. And I wanted to call it dusty because it does get very dusty. It's a dirty thermal vacuum chamber. You're allowed to play with ice and dust in there to a degree because some things are bad for the pump. And so the chamber is used to simulate dusty or icy surface processes on Mars or other planetary surfaces. And it was originally used for preliminary prototype Phoenix RASP tool testing, which is very cool. I feel like I'm working with a piece of history.
Yeah. You are, except it didn't have a name before that, despite being around since Phoenix?
It was called, I think it was like lovingly called the 2-foot chamber in Building 117, JPL. Yeah. So I was like, this got to get a name. This is a pretty cool chamber. And we recently upgraded it with the hopes of more planetary scientists using it for analog experiments. So I was involved with an effort to do that, working with some great engineers at JPL. And so I said, okay, guys, we gotta give it a name.
Is it one of those situations where it's best used for Mars and you would create similar facilities for other worlds so it's, kind of preset to those conditions? Or do you just have one that you dial to, today I want it to be like Enceladus. Today I want,
That's a good question. Yeah, the chamber has been modified for other experiments, related to small bodies that I got to be involved with, led by Jennifer Scully at JPL and Michael Poston at SWIRI. So that was some really fun work looking at transient brine activity in the chamber. So those conditions were much lower pressure. And then also some other folks are doing experiments where they're using a turbo pump to bring the chamber to lower pressure than Mars pressure as well.
Oh, man. I feel like I would have so much fun playing with that. Every time someone tells me they get to do these experiments in the lab, every time I'm like, I want to go shoot things at a meteorite or put it in the strange Titan chamber you created. That sounds like so much fun.
Yeah. I'm going to have my own lab soon where I'll have my own 2 vacuum chambers. So I'll have more free time to if I'm curious about something, just to put it in there and test it out, which will be great. I'm looking forward to that.
That's going to be so fun. You're going to have the best time having your own, like 2 vacuum chambers instead of 1.
Yeah, I'm going to have 2 separate ones just so that one is kept a bit cleaner than the dirty one because, you're going to have problems with your pump and trying to keep it healthy for the more clean conditions.
What are the most important parameters that you're kind of calibrating in one of these chambers to make sure that it's as Mars-like as possible for this kind of experiment?
You're basically trying to control pressure and temperature to try and make it like, for my application for Mars winter or springtime conditions. So targeting average Mars pressure of between 6 and 10 millibars, and then targeting the temperature at which CO2 will condense on the surface, which had already been identified by my collaborator Anya in her previous experiments. So she has a nice graph that shows where the CO2 will deposit on the surface in its translucent form. So we basically had that to go off and just targeted those temperatures and pressures. So you're able to cool the chamber with liquid nitrogen, which flows through a cooling plate at the bottom of the chamber. And then there's a shroud that it also flows through, which cools the sky, which is very important for Mars polar experiments, because if you condense CO2 and the sky is too warm, it's just going to sublimate from the top. So dusty is a nice little chamber for it's the right size and the right temperature condition. It can get to the right temperature conditions for investigating CO2 processes on Mars.
What kind of regolith simulant did you use to do the experiment?
Yeah, so we used Mars Mojave simulant. There's lots of it up at JPL. There's these big vats of MMS just sitting there, so that's great. So we used that, and in some experiments that we're running at the moment, we actually sieved it to look at the influence of different grain sizes on the CO2 that's condensed, and then possible morphologies or plume activity.
Yeah, I imagine if it's more grainy, you gotta have a really strong jet in order to burst it forth.
Yeah, so it's the heavier grains that the plumes end up being more diffuse, and then the finer grain sizes, the plumes reach the top of the chamber and they sort of keep going.
Yeah. I mean, given the size of these formations, I would personally guess it's probably dustier, smaller pieces, but who knows? I mean, I haven't been to Mars. Yeah, that's cool. So you end up with this Mars simulant in a container in these Mars-like conditions. Then you tried to create enough CO2 ice on top. Mm-hmm. how did you try to create this situation where in the Kiefer model, the sunlight is coming through, and that is what's producing the heat that's actually making the ice sublime from the underside, essentially. How did you reproduce that?
Yeah, so great question. And the sunlight step is the next step. I'm super excited to eventually use like a solar simulator. But these experiments are very difficult. There's been multiple steps we've taken to perform these experiments. My first experiments investigating spider formation on Mars were done in like 2018, I think, around the end of my PhD in the UK at the Open University Mars Chamber. And we just got blocks of CO2 and put holes in the center. And we put them in contact with room temperature sand. And we looked at the spider patterns. And then so the next step was to try and actually just naturally condense that CO2, which is a whole other process in itself. Yeah. So at JPL, we've been trying to figure out the right methodology to condense CO2 and then heat it from its base. And so we're doing it step by step, because in experiments, if you try too many things that are unknown at once, then it's just a mess. So the last experiments we did, we condensed CO2 on Mars regolith simulant, and we used little heaters beneath the substrate. So it's not as accurate as we'd like to get it to the process on Mars, but we're getting there. So we had these little strip heaters embedded below the surface. We flowed in CO2 gas once the chamber was pumped down and cooled to the right conditions for Mars. And we built up this layer over about 4.5 hours of CO2. And what we actually found was that the CO2 diffused into the top layer of the substrate. So the Kiefer model suggests that you have this layer of CO2 ice on the surface, but hasn't really investigated so much how the CO2 might actually diffuse into the top layer and how that affects dynamics. So there's quite a surprising result from the experiments in that when we activated the heater was actually heating CO2 ice that had embedded in the top layer of the substrate. So if you actually take out a chunk of the regolith after the experiment, you can see that it's very consolidated. There's ice within the regolith material. And then you have a top layer as well. It kind of looks like an open sandwich when you take it out. You can see that the regolith is cemented, and then you've got this nice kind of whitish top layer of what was originally translucent ice on the surface. So yeah, when we activated the heater, what actually happened was the CO2 within the substrate cracked. So we got these cracked spider-like patterns, which are very different to the spiders I saw in my PhD, which were formed purely by surface scouring. And so we thought, maybe this is an alternative formation mechanism for some types of morphologies of spiders, because you have a whole wide range of different spider morphologies. Some of them have thousands of branches, and I've actually counted those. It's tedious work. And then others, they have very wide centers, and they might have 10 branches, without many orders trailing off from them. And some of the spiders on Mars, particularly the dendritic troughs that I was talking about early on the interdoom material, they appear kind of cracked-like. They look similar in morphology to what we were seeing in the lab. And so we came up with a new hypothesis for maybe an alternative spider formation mechanism where there is either CO2 ice or perhaps water ice, and we'll have to investigate the sublimation of water ice in the lab. But basically, if you get ice sublimating from within the regolith, you can get this kind of cracked morphology.
Does the grain size of the material change how much of it ends up being filled with these bits of dry ice?
That's some work that we're writing up right now. So, yeah, sneak peek to that is that it does appear to affect how the ice grows. There are certain grain sizes where it appears that for coarser grain sizes that the CO2 does diffuse, but not to too much of a degree. The top ice layer grows in from the sides more readily. And then for the finer grain sizes, the ice appears to grow upwards from the base in the lab. But it's important to note that the conditions in the lab are slightly different to those on Mars, right? We're cooling from the base. So we have a tray of Mars regolith simulant that we have plonked on a liquid nitrogen cooled plate. The liquid nitrogen is cooling that from the base the whole time. And on Mars, we don't think there's anything cooling from beneath the regolith. So the conditions are slightly different, and the thermal gradients will be different as well. So you have to take everything with a grain of salt.
This is why I am so sad that the mole probe on InSight didn't manage to dig as deep into the ground as we wanted it to, because understanding more of the thermal properties of the soil, I mean, that I'm sure it changes from place to place, but even that amount of data would have been a good point in here and so much other research.
Yeah.
So what did it actually look like by the time you were done with this experiment?
Yeah, so when we finished the experiment, we let the plume continue on in some experiments just to see how long did it last for. Did it reach the top of the chamber? We kept it going. And, when you let the plume keep going, then you're erasing the surface material because the dust is then falling back on the surface and you can't see what it's actually formed. And that's another interesting insight from the experiments as well. It sort of led us to think, well, the timing of the plume activity would drive whether the feature that's produced is actually preserved. So some experiments, we kept the plume running and the chamber was just full of dust and the ice on top was full of dust. And then in other experiments, we stopped the heater right when we saw the cracks form because we wanted to preserve them. And so we backfilled the chamber very carefully. So backfilling is basically allowing nitrogen gas into the chamber. You could use air, but that's introducing water vapor. So backfilling with nitrogen gas and bringing it up to atmosphere again. So the door opens then when you're at atmosphere and you can look inside. And in those cases, we had some ice left on the surface. There was some CO2 ice left on the surface. If you dug into it, you could take out a chunk, and there's some images in the paper of me holding one of the chunks, and you can see a top layer of CO2 ice on the surface. And then right where the heater was, you can see these cracks that formed from the activity. Yeah.
I also read that there were some kind of interesting halo formations. Yeah. Well, what were those?
Yeah, so we around the edges of the heater, there were these kind of white circular halos. So we also got fans and spots, so you could see on the surface the material which had fallen down on top of the ice appeared darker. And then around the heater, we had these bright kind of frosty edges. So we think that some of the dust that sort of flew up from the plume in the chamber atmosphere, some CO2 basically adhered to the dust and fell down at the right temperature conditions around the heater and formed as kind of triangular frost crystals, forming these halo-like features. And we do see kind of halo-like features on what are known as fried eggs on Mars. They're a particular type of spot where you have your traditional dark spot on top of the spiders or elsewhere, and they've got these kind of whitish rings around them. So we didn't investigate them too much, but they were an interesting observation all the same.
Yeah, it'd be interesting to know how long those last and whether or not we could look for those as an indication of like recent activity.
Yeah. I'd be interested in better constraining the conditions under which they form.
Yeah, that's really cool. What happens next? I know now you're going to be trying to replicate this with kind of more sun-like conditions rather than a heater, but what other things are you curious to change up and see?
Yeah, so there's a whole host of things we can do with spiders still, and I'm super excited. I have plans to continue these types of experiments, but then move to the next step that I was talking about, using a solar simulator. So I'm going to be moving to the University of Central Florida in February, and I'm going to have my own lab there, which I'm really excited about. And I plan to install a solar simulator on top of a Mars chamber and basically shine it through the CO2 that I've grown and investigate what, if any, do we get any, similar dynamics to those that form spiders, and what are the right conditions, and how does dust within the ice affect that as well?
This is a good opportunity for some comparative planetology, I feel, because, we can't really compare it to Earth-like formations, but there are some formations that are very kind of spider-like on some other worlds. I'm thinking primarily of Europa. Understanding how this happens on a terrestrial, kind of less icy planet is one thing, but it's still very meaningful, and we can compare it to these other worlds. Is that some of the science that you're hoping to do?
Oh, absolutely. I'm a big proponent of comparative planetology. So there is a spider-like feature on Europa, but it's a very different feature. It's more asterisk shaped, and I have been conducting a study to try and investigate that as well. And I'm also interested in the lake stars on Earth, which I've been using as an analog for that feature.
What do you think causes the lake stars? Because it's not CO2 ice, it's not necessarily subliming. How is that happening?
Yeah, lake stars are beautiful features. If you're ever out near a frozen lake, check them out. I feel they're way too understudied on Earth. There's not that many papers on them. And I became fascinated by them a few years ago. I'm actually just back from a trip to Breckenridge. We go each year, and I end up going out onto the lake, looking at them and imaging them and trying to study them. They're basically dendritic-looking features that appear pattern-wise similar to spiders. So they have that same branched pattern, but they actually form by a very different process in ice. They form when snow falls on a frozen lake, and you get a thin layer of ice on the surface, and then eventually the relatively warm water beneath the lake ice wells up through a hole in the surface, and it spreads out through the snow or the slush. And basically that dendritic pattern is a very common pattern in nature, where you've got a gradient in the system. So on Mars, you're dealing with a pressure gradient, right? You've got pressure going from high to low. And on Earth, you're dealing with a thermal gradient driving that pattern. So it's essentially like an energetically favorable pattern when the system is trying to stabilize. And so it's the pattern that forms when water melts a smaller snow particle faster than a bigger one, and it's the melt pattern of the water welling out, and then eventually the system freezes, and you've got this beautiful dendritic pattern encased within the ice.
That'd be so beautiful to go see.
Yeah.
Are there any particular places you see them more often than others?
I think I thought they were super rare. Mm-hmm. When I first started studying them, when I came to JPL, I thought they were really rare from what I was reading. And coming from Ireland, I don't see a lot of snow. We get snow maybe once a year. So, and I hadn't seen them. And then we went on a vacation to Colorado, and my husband said to me, I was asleep, and he said to me, "Lauren, look, there's lake stars outside the window." And I thought he was saying, "Come on, get up, there's George Clooney's outside," I thought he was trying to get me up and out. No, there were literally lake stars on the lake outside the window, which was amazing. I was so excited. It was like I had seen a celebrity. I got very, very enthused about this. And so, yeah, each year we go to Breckenridge and we see them out there. I haven't really been elsewhere that I've seen them, but I have seen images of them from Alaska. So I think it's anywhere really where you've got a frozen lake. And a colleague told me, I was out at a conference, and I was burning someone's ear off about lake stars, which I like to do. And he said to me, "That's what they are." "Oh, right. I've got a whole album of them on my phone. I've been showing my students them," and they had them there apparently in Boulder. So yeah, I think they're more common than I originally thought. And in talking to people about them, a lot of people have been like, "Oh yeah, I've seen them," but they're not as fascinated with them as me. So yeah.
So you've done all this research, and it's told us a fair amount about how these things formed. But coming back to that weird original question of where they form on Mars, does this give us any insight into why they form primarily in the southern hemisphere, or is it still a mystery?
There's still a lot of mysteries surrounding Martian spiders, and there's still a lot of research to be done. Why they form in the regions that they do is most likely driven by grain size, ice thickness, and the translucency of the ice. So how much sunlight can get through that top layer of ice.
Well, I'm glad now we know a little bit more about how they form, so people don't have to panic. They are not actual spiders on Mars. Thanks for coming to Planetary Society headquarters to talk with me, Lauren.
Thank you so much. It's been wonderful to be here.
And now it's time for What's Up with Dr. Bruce Betts, our chief scientist here at the Planetary Society. Hey, Bruce.
Sarah.
Oh, gosh. So quiet.
Mars spiders.
No, did you hear?
Scary.
It would genuinely be horrifying if there were actually spiders on Mars. I straight up double took the first time I read one of the article titles back in the day. I was like, there's no way they're talking about spiders on Mars. And then I was like, oh, They're not talking about spiders on Mars. They just kind of look spider-esque. Now knowing more of the mechanisms that are creating these kind of spider-like features on Mars, there are some other things in the solar system. There's some spider-like-ish features on the surface of Europa and places like that. So it'll be cool to see them compare them all. But what I'm really interested in is the fact that there are these kind of seasonal changing bits of geology on Mars and trying to figure out whether or not that's all about carbon dioxide or if there's some water involved. There's a lot of mystery there.
Why, yes, indeed. There are actually many changes that occur, most notably those big polar caps, but I'm guessing you're referring to recurring slope lineae.
Those RSLs. It's true. I mean, everyone kind of lost their mind in the space community when they were like, oh my gosh, look at these features. They're running down slopes. They look like maybe liquid water's involved, but I don't know. What is actually going on with the RSLs?
Well, if I knew that, I would publish a paper.
I know, right?
But I can tell you what the discussion is, and I may be a little behind. So if people found out that it really was aliens, as we suspected all along, let me know. RSLs are, as you say, they occur on slopes, typically like interior crater slopes, sun-facing direction often between the equator and mid-latitudes, and they tend to be dark streaks that occur during the summer, the balmy summer, which is not balmy at all, of course. And so there was a lot of thought initially that, hey, maybe these are liquid water features. So that's the big deal. Mars, the atmosphere is not stable any longer because of the temperature and pressure. You just have water acting like dry ice on Earth, going from a solid to a gas to a solid. But liquid water is what makes the astrobiologist giddy, because that's required by all life on Earth. So the fact that you might have some liquid water on the surface is exciting. More recently, the theories have favored dry flows, so sand dune type flows, when you see something run down the side of a sand dune. This is based mainly, as I understand it, on the slope and the fact that it's very near the angle of repose that you would expect for loose grains. So basically, you have to get sand dunes to 30-ish degrees slope, plus or minus a few degrees, depending on factors, and then they will slide down, they'll collapse. But water can go flowing at low angles and high angles. So the fact that they only found this at high angles tends to make them think that it's granular flow. But wait, there's still the curiosity of all sorts of things, including what starts it. Maybe there's a little bit of water or something that starts it. They also have found hydrated salts at some of these locations, which may be caused by water, but it may be water from the atmosphere, and it may be this and it may be that. And so it's a great groovy mystery in terms of the details, but it's less dependent on thinking liquid water, but it's still in the game. Whew. Sorry, that wasn't a very short summary.
It's all right. Any feature that changes from season to season on Mars is fascinating, given its history and what we don't know about it right now. These araneiforms, or the spiders on Mars, they don't disappear from season to season, and they don't seem to grow or for more of them to sprout. So there's a lot of mystery to when they formed and how they formed, but these RSL change from year to year. So who knows if they're connected, but that being said, Mars is a weird place. I so want that Mars sample return mission.
Well, all the other missions are doing good stuff too. But yeah, Mars is, I love Mars. It's fascinating. But enough about that. Whew. How would you like a little bit of a random space fact?
Classic. Is it about spiders, though?
No, but it is about things that will crush you instantly.
That's cool. That makes it random.
No, I really went random this time, and I flew off to neutron stars, because
nice.
They're always a good time, because they're super stupid weird. The gravitational pull at the surface of a neutron star is about 2 billion times stronger than Earth's surface gravity.
Yikes.
That's a lot of gravity, my friend. All right. Everyone go out there, look up in the night sky, and think about happy little flying butterflies that can't hurt you. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with a review of space exploration in 2024. We'll bring on the Planetary Society crew, including Planetary Radio's creator, Mc Keown. And since I know a lot of you are going to be traveling in the coming weeks, I want to mention that we're kicking off the new year on January 1st, 2025, with our first Planetary Society 45th anniversary episode. My guest will be our CEO, Bill Nye the Science Guy. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, poetry, and your favorite space gifts to give people at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members who love a good Martian mystery. You can join us and help support the scientists and the missions that are cracking the mysteries of Mars at planetary.org/join. Mark Culverta and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.